Hello everyone, this is JA Solar Power Talk, connecting experts, delivering insights. My name is Zi Ouyang, the Chief Technology Officer of JA Solar. Today, it's my great honor to have Professor Bram Hoex here, the Deputy Head of School of Photovoltaics and Renewable Energy Engineering of University of New South Wales. And Professor Hoex is a world leader in many ways of photovoltaics, and he has a lot of innovations. I think one of the most important one is he invented this aluminum oxide passivating layer for both PERC solar cell and TOPCon solar cells, which one was the most popular one and the one that is dominating the market. So I would say Professor Hoex is very important person, and again, it's our great honor to have him here to give us this talk and the conversation. And with over 250 papers, which is amazing, and an award like IEEE Young Professional Award and Solar 40 under 40 plan just brings lab science with real-world solar technology, especially TOPCon. So welcome, Professor Hoex.
Okay.
Yeah. So maybe I start with a question, Professor Hoex. Why do you think TOPCon is now the most dominating and so important in this industry? What's fascinating about it? What's the magic behind it?
Yeah. Well, thanks, Ouyang, for first of all for inviting me for this very nice series, the Power Talk, and having me here at JA Solar again. TOPCon was actually the natural successor of PERC. So PERC was dominant, from let's say the early 2010s to let's say the early 2020s. So it had a good run for a decade, and the PERC solar cell was actually limited by its efficiency for the electron collector, so the phosphorus diffused emitter. So that was holding it to the 25% limit. So we had to find another way to get the electrons out of the solar cell. And the TOPCon structure, which was actually invented, or the first way it was implemented, like we do in the TOPCon solar cell, was actually done by Martin Green at UNSW, where we both have worked. And I still work. He did the first TOPCon contact in the 1980s, and this was based on his earlier work of metal insulator semiconductor solar cells. So these are contacts that are passivating and a contact at the same time, so the so-called passivating contact. And that enables you to break through the PERC efficiency limit, which was around 25%, and which was limited by the electron contact, because the whole contact for the PERC is actually quite good. That would enable 26-27%. It was really the electron contact that we had to fix. So that's where we went back to the history books and to the literature, and saw that these metal insulating semiconductor contacts, where TOPCon is one of the best variants of that, performed a very good solution. So we just changed one contact, and because the TOPCon contact, we use polysilicon, which has a relatively high absorption, we could not put it at the front, so we put it at the back, and that also meant we went from P-type base material to N-type, and from a phosphorus diffused to a boron diffused emitter. So we're a few steps, but they were the step change was a lot smaller than if we would have started directly to heterojunction technology, which was the main other technology that was being considered at the time.
So it's a nice marriage. From on one side, it has a history from PERC all the way to TOPCon, and secondly, the technology building itself, it's pretty good.
Yeah, and a lot of the technology that we had for PERC, we could still use. You just refer to my work on aluminum oxide, and that one for the PERC solar cell, it was at the rear. For the TOPCon, is at the front.
Yeah.
So, but it's basically the same technology. Silicon nitride as well. So boron diffusion is more complicated than phosphorus diffusion, but it was doable to do that, and the type of equipment is actually not that difficult. So for you as producers, it was a relatively easy transition because a lot of the equipment was similar, and some manufacturers actually use part of their PERC lines for TOPCon. Although if you could afford it, you would buy.
Yeah, I mean, it's just I mean, you have one more laser process, and you either use PCVD or LPCVD for the poly. Poly is amazing if you think about it. It can both attract the majority carrier and shield away the minority carrier at the same time, at the same place. We call it carrier selectivity, right?
Yeah.
So is that one of the best materials has some such great selectivity?
There's a few others. So we have the silicon-based route. So high temperature is polysilicon, low temperature is amorphous silicon. So heterojunction. So heterojunction and TOPCon are probably heterojunction slightly better in terms of recombination, but they're very similar. So it was a good benefit. They're very thermally stable. So that resulted in TOPCon really being the winner. For heterojunction, initially there was the patent issue, but then there were also a lot of new processes that had to be developed, had to be further optimized, which made it still a more difficult technology, a lot more expensive.
Yeah, you just mentioned the efficiency and the performance. That's truly amazing. I mean, in our lab, our most efficient solar cell, TOPCon solar cells, we have 749, just one.
Yeah.
All the way from 750. That's we're trying very hard, and that's also one of our targets in our R&D team. We want to surprise you again in this year's. Let's see what we can do on the efficiency table. Yeah. We have a plan.
I'm very interested in that. Now I'm very familiar with your result on very close to 750, and that's amazing. Even a few years ago, I would not have thought that this was possible with TOPCon. So with one passivating contact, because the front of the TOPCon solar cell is still diffused with screen printed metal. But the introduction of laser-assisted firing has really enabled, really pushing that the boron diffuse emitter to close to its limit. And the difference with heterojunction, it's very small. And then optically, of course, the TOPCon structure has always been better on the front side. So rear side, of course, we have some parasitic absorption, but you have great technology, I know, in the pipeline to address that. So TOPCon can really, because I think what's your current world record is around 26% for
more than 26%. We haven't published yet, but we'll just let you know we're above that.
Yeah, no, that's amazing. And these are certified efficiency, so these are not reported efficiency from the production line. So because there has been some over-reporting in the past by other groups, but this is really certified efficiency. So that's really amazing, and it just shows the potential for TOPCon also for the future. Because of course we will not stop here. There's a lot more to do.
Now we have more to do. That's probably another question I wanted to ask you. What do you think? What else can we do in the next couple of years? I mean,
so in order to push TOPCon to its limit, it's always about reducing losses. So we can probably in manufacturing get to like 28% if everything goes well. So you're at 26.x, so there's still a bit of room. So where do we lose it? It's optics.
in some top end.
Top end, yeah. So the poly fingers, what we mean by that is that at the rear of the the TOPCon solar cell, we only leave the polysilicon under the metal contacts, and then in between the metal contacts, we remove it because we actually don't need it for the solar cell to perform efficiently. It's more difficult to manufacture, so that's why this was not the natural first step. But the problem of having poly at the rear outside of the metal is that you actually have part of the light that you can still use for the solar cell is not fully absorbed in the first pass. And part of that light gets absorbed in the polysilicon, so it gets lost. But the most obvious one is, of course, for rear illumination, because all solar cells are bifacial. So they collect sunlight from the front and the back. The best locations in the world, we have more than 20%. There's some tricks to where you can push that. So that rear performance really increases if you remove the poly from the rear. Yeah,
That's your invention again.
and that's actually. So from a fundamental point of view, it's not the first one we think of because of the mechanism. I'm not for the audience, so that's why we still have room. But then the second part is, and it's a big matter as well, is the recombination. Because recombination increases VOC, but it also, from a fundamental point of view, it gives you a higher fill factor, more than you would expect from the first principle, because your solar cell changes from defect recombination limited to J recombination. So your solar cell, your TOPCon solar cell is already, so you would be already like 50%.
So what the winning is not only about the VOC, but also on the fill factor.
Fill factor. Yeah, you get a big
So the
boost.
curve will be more squarish.
Yeah, and that's where we have to go in order to get to that fundamental limit. But then, that will really be the end of the single junction limit. And then we need to add new functionalities. And there's a few flavors that we that Jay and also of course UNSW is working on.
Yeah. So that's pretty cool. You just mentioned the optics. One of the important things particularly for bifacial metallization is to reduce the shading loss at the front. But we will jump to back contact later. And for TOPCon, just to let you know that we actually are developing amazing technology, metallization technology at the front with aspect ratio can be more than 1. Wow. So that's it's still in the lab, but I think you will see that in the market pretty soon. And actually, we have been using that on our efficiency cell in the lab already. So we're on the way, actually pretty close to mass production, use that technology. So hopefully we can squeeze a little bit more from the efficiency.
Can you comment on how narrow your lines are becoming? Is it?
It's very, very narrow. Yeah, it's we can do it like less than 10.
Less than 10?
Yeah.
With screen printing?
Well, it's not.
I'm not. Yeah, I know. With industrial technology.
Yeah.
Oh, that's very
We'll
cool.
see. Yeah. Maybe I will show you after the talk.
Okay, that's good. Yeah, because a lot of people don't realize is that they're so the front cell metallization, when you do the cell testing, it's full loss, of course. So whatever percentage you have covered with metal, if it's 3% or 5%, that's 5% loss. But a big part of that reflection you can tune to come back to your solar cell. So the metallization, so the initial loss you have due to metallization, part of it comes back as a cell to module gain.
Yeah.
So if you do it well, so that's also. If you don't take that into account, then you would not understand the full potential of front and back contacted solar cells. And we did some initial analysis. That was in when I was still working in Singapore. So that was contacts that would look more like a pancake than your beautiful contacts with a 1-to-1 aspect ratio. But that was already 50% of the light that is reflected from the metal actually ends up in the solar cell. So it means that your optical losses on the front, you can significantly reduce it. So even your metallization loss at the cell level it's 3%, maybe at the module level it's just 1.5 or 1%. So you can tune that there as well. So that's also, so you don't necessarily have to go to all back contact to get the full.
No, actually, it's like that.
Yeah.
It's like that.
Yeah.
It's more like this. It's like that.
Yeah,
So give you a second chance for redirection.
That's a good way to do it. These are I think they were coined effectively transparent contacts. So they're for concentrating solar cells. They make a lot of cells. We have a lot of current, and the light is very directional, so that it's easier. But yeah, it's a good technology.
So maybe we talk about since we're already at the metallization side. Let's talk a little bit about the shocking silver price.
Yeah.
What do you think?
So it's of course it's a lot of speculation. So it's not. We're a bit unfortunate that we use silver material that's also used as for hedging against political instability. However, it's just transition of it's just asking the industry question that would have been asked anyway. So, because we could not continue with the solar consumption that we have in terms of with the growth that we want. So we have to talk solar consumption. Now with the high prices, which is a lot on the stability of PERC, TOPCon, petrodotion, just to understand what can affect the long-term stability of these technologies. And we focus a lot on in recent times on metallization, where we mostly see interaction with everything but the silver, but selected critical components, for example. We haven't really fully explored what would happen with all the copper containing technologies, for example. So yeah, there's a lot of Suntech, BP sector. So, and in the BP sector, they found out they study modules from the 90s, and they were still staying. Of course, it was a quite different technology, but which probably would have been more robust, but it definitely shows that copper can be stable. But
It's just to give the audience a bit clue, and copper, if you don't do it properly, it can be a killer to the solar cell. The diffusion into the silicon doesn't like it. Diffuse to the encapsulant doesn't like it. And as we know, Professor Hoex is one of the world leaders in this area. Actually, he himself and his team have done a lot of work on the reliability of the solar modules in different environments, very harsh environments, and we actually worked together for quite a while, and we published a few nice papers together on the damp heat degradation mechanism for silicon, for glass architecture and glass backsheet architecture. So his work and his research is very important. Maybe you talk a little bit more on it. I heard you've developed some very nice way and a quick way to sort of have early detection of the failure mechanisms. I mean, we are very interested because sometimes we develop new materials and the designs. We want to have a relatively quick answer. We do not necessarily like the accelerated test. We want to accelerate a bit more.
Yeah.
Can you introduce a little bit on your work?
Yeah, well, so our approach is it's also asking ourselves a question, like with industry players like JA Solar, like we just had to take a car from where we had our meeting to this building because your site is so big, and you say like there's heterojunction pilot line, perovskite pilot line. So there's so many capabilities in industry. So what kind of value can a university bring? And of course, we have typically a bit more time because we're not selling products, so we can take time to solve issues. We're typically very good in modeling, so so fundamental modeling of solar cell design and then degradation processes, and we have a lot of characterization tools. So these are techniques that a company would never invest in. So we then decided looked at how can we then provide value to the industry, and that's really understanding failure modes. So of course, when an industry partner sees that certain material combination is not working, you would just quickly cancel that vendor or not use that material. But for the field and also for the industry, for yourself, it would be very important to understand that. We have the time to do that. So we do a lot of tests. In recent years for TOPCon, the TOPCon solar cell was the main sensitive part because particularly the front metallization was quite different. So the boron emitter had only been used in PERC solar cell, which was only a few suppliers, so it was not as mature. So there the industry really did a lot of innovation, but unfortunately some of these innovations made it a lot more sensitive to corrosion. And that's where we got a lot of publications, a lot of press as well, because we showed that some choices for TOPCon made them very, very sensitive to corrosion, which is significant. And we related that back to additives in the metallization phase. And that provided the industry a good insight. Okay, that's something we have to work on. Yeah, it was aluminium, which is quite interesting. So aluminium is not always good, and aluminium oxide in a paste, definitely not. So when people moved away from that really significantly improved the stability. So then there's still like the fritting components are also a high sensitivity, and also there we drill down in what elements. So is it the lead oxide or the other all the other oxides that are being used to provide good contacts? Are they incompatible with certain materials you use in manufacturing or in compounds that can enter the solar cell or be or enter the module or can be generated during its lifetime? So, and that's our corrosion research. But another topic that that was of course the biggest topic of last year was UV-induced degradation. Because like for the audience, so certain TOPCon, so not the JA modules, but some other vendors, they after giving them an equivalent dose of 2 years in Sydney, they degraded by 10% just because of UV. And that's of course the whole market was shocked by that, and there was also a big range. So the best manufacturers maybe a little bit worse than PERC, but some of the outliers really scared the market. And another complication was that people, the way you tested it had a big impact on the result you measured. So a lot of people do testing. So you stress the module with UV, and then you put it in the line to be measured, and that could take 1 week, 2 weeks, depending on how busy you are. And unfortunately, if you measured a module after 1 week, it looks a lot worse than if you would have measured directly. So what is the proper way to measure, and where is this instability coming from?
The meta-stability issue.
Yeah, so the meta-stability, I will not explain it here because that would require a lot of time, but I just explained to your team the whole model behind that meta-stability and microscopic origin. And with this model now, companies like JA and certification agencies can define the right testing procedures and also demand that for their clients if they would do independent testing to ensure that they measure the appropriate value. So UVID is still probably the problem is not as big as it was reported because some people because they did not have the knowledge, tested it in the worst possible way. And now this insight is also reflected in the new standards, so the new IC test.
Yeah, that's pretty important because
we're working on as well.
But we everything we do in the lab is basically trying to mimic in the best way to the reality. As you said, you store the modules in a dark room for a couple of weeks. That's not going to happen in the field.
No, that's not going to happen in the field.
Yeah. And also, I know for UV testing, actually, if you don't do it properly, the dosage can vary a lot.
Yeah, that's so it's quite complicated. We also showed that us and others, so the National Laboratory of the Rockies, the former NREL, probably did the best work there. They showed the impact of the different wavelengths of UV, and the higher the energy of the UV photon, the more damage it does. So if your light source is still within standard, but has less of these higher energy photons, then even with the same standard, that's easily a factor of 3, probably even more. So it's really difficult to do apples as a university with this fundamental research, which takes a bit more time. So in a company, you would probably never have time to do that, but we have time to understand this model, and then we share it to the world because we want to ensure that people are aware of the full fundamentals and can really use that to accelerate the deployment of solar, because we want to see solar power the world, and for it to do that, people have to trust it. And these kind of failure modes can really take away some of the trust. Because I know for UVID, at a certain time, German banks stopped underwriting TOPCon projects. That's just because of one failure mode. That's massive. I think they've gone back again to underwrite it. But yeah, that's, and I've heard from some of the people in the field that our work has been helpful in that, to take away that, okay, it's a problem, but well, let's get real. This is what it really happens. This is how you can do proper testing. And what we're working on now is how, even for stuff that's fielded, we want to then be able to predict specifically for that location, because unfortunately, that's how granular it will be, how bad it would be, and then the asset owners can make their decision.
Yeah, I think it's very important that Professor Hoex mentioned now. TOPCon has one name, but there's many variations of TOPCon in the field. Like we know JA, our recipe of the depositing like aluminum oxide, for sure will be different from our competitors, because that's kind of secret for everyone. That which means UVID is a problem, but if you do it properly, you have a solution. Yeah. That's typically for most of the degradation mechanisms. That's why your job in understanding them is very critical.
Yeah, I think of course with so companies would mostly be driven by like just design of experiments, etc. Like they see that certain things work, but then not necessarily have the time. You would have to move on to the next problem, and then before you can fully understand it. So that's where we can help, and that's why industry academic partnerships are super important. But definitely, like so based on our work, of course, we're working with quite a number of suppliers as well, and we also do ranking of UV sensitivity of TOPCon solar cells, and there's a massive difference. I will not mention names, of course, but there is a big difference between supplier to supplier. We do the testing at the cell level, because of course there are also mitigations you can do at the module level, which many manufacturers do. So indeed, it's not just one TOPCon. It's one brand of it's one name, but it's a architecture, and all the leading producers have their own unique technology, their own unique patents. So it's not it's not identical. So just the fundamentals are roughly the same, but the execution is slightly different.
You just mentioned the UVID, right? That's maybe allow me to jump the topic again. So we actually now the space photovoltaics is a hot topic, and UVC, of course, is a big problem for that. And we know there are a lot of problems like a thermal shock and also oxygen atom bombardment, all the other stuff. How do you think the space photovoltaics, is it still quite far away, or
No,
what do you think?
like we know for sure that like the largest number of satellites are powered by silicon PV. So that's mainly low Earth orbit. That's older technology, so probably not heavily adapted. So definitely silicon can do it. These challenges can be addressed. So one of the main sensitivities, of course, radiation-induced damage. So in addition to UV, so which is let's say you maybe go to 6-7 electron volts, but you get 1 mega electron volts interaction there. So that creates really defects in the silicon, which you cannot avoid. So because if you would putting a barrier for that would be too expensive, and your solar cell would probably not see any light. So that's something you also have to address. So that's something we're working on as well as UNSW. So we look at self-healing silicon. So we have technology for that. So you cannot avoid the radiation damage, but if you can recover it, that helps. And also, I think the excitement now about space PV is really due to, so internet. So having space-based internet, but then also AI data centers. Because it might, for many of you, it might sound a bit like science fiction to put AI data centers in space, but it's actually, it makes perfect sense because if you have the right orbit, you have the sunlight 100% of the time. So we have more sunlight here than, so even on the sunniest part of the day, you get 30% more in space because of the atmospheric.
AM0, sorry.
AM0. So you just have more light, you can have it all the time. And then what is a big problem for AI data centers is cooling. So of course, when you face the sun, that's hot, but space is very cold. So radiative cooling, if you can manage your system in an appropriate way, you don't need to have active cooling. So the running cost is actually quite low. The cost of sending stuff to space has come down tremendously with reusable rockets. So predominantly, I think the only company now is SpaceX, but there will be more. So I'm very bullish about space solar as well. And then we're going to set up bases on the moon, which will be a lot more challenging than LEO. So low Earth orbit, you're still protected a bit by the planet, but if you go outside of that, it's a lot harsher. So it will be a bit more challenging on Mars as well. So I'm very excited, and I hear there's a lot of excitement in China at the moment. So.
Well, I would probably say there's more noise than what people are really doing. I'm sorry, I shouldn't have said that, but in JA we actually have done quite a lot of research, but we know we are getting closer and closer to the real application of space photovoltaics, but we'd rather solve the problems in-house one by one. So before we can announce, okay, we are ready, I think we are not ready, but we are getting there. Just for example, just for what Professor Hoex just said, we have to have protective glass to shield most energetic
The protons.
in the protons,
Yeah.
and we have to develop wafer thin cells, so some of the energies can go through instead of staying.
Yeah.
And outgassing is another issue that we have to solve. And the p-type material at either p heterojunction or p-PERC. Well, that's the choices, and maybe if we want high efficiency, then perovskite and silicon tandem as well. We are trying all these things, but I think we're definitely interested, and we're working on it.
Yeah. No, I think the AI boom has really changed the whole discussion because it's just a total addressable market. So it's a business term, but yeah, you're running a company, so it just has exploded. So if you just look at the applications we had before AI, the TAM would have been a lot lower, but now with AI, the short-term addressable market is a lot larger. So that explains the excitement. But yeah, we've done as I mentioned, we actively work on that with also an industry partner in Australia, and yeah, we're quite bullish about it, and the bullish about the potential of even silicon. So for perovskites, it might actually, yeah, like if you look at the typical lifetime you would need in space, it's shorter than terrestrial. Perovskite, of course, with its intrinsic insensitivity to defects, yeah, even the defects you form, yeah, so that makes it quite a promising material, but there's still a lot of challenges that we have to solve with perovskite. But it may actually be for space because you just need 5 years typically.
Yeah.
That might be earliest market fit for.
Yeah,
for
5 years. That's actually very important. Is when we do R&D and product design, you really have to understand the working scenario, where the project is. Bram just mentioned that 5 years, so there's no point if you try to develop a 25 years lifetime stuff because the satellite itself won't last that long.
Yeah.
So it's interesting. Then maybe let me switch the topic again since we mentioned about the application. I heard you have another exciting research project on kind of the full supply chain, simulation or evaluation of the power generation capacity over the years from cell all the way down to power plants.
Yeah. So because it's partly informed by the fact that we do a lot of publications on cell level, module level, but of course people are asking me like if I speak to developers or insurance companies, and it's like, what does it mean at the final yield level? But even if you look like this, if heterojunction technology would not degrade, then even the standard simulation packages like PVSys cannot predict the performance accurately. So because the way they model solar cells is, was informed of what was necessary for aluminum back surface field and PERC. So there are some shortcuts they make, which if you don't make them, you actually significantly reduce the uncertainty. And this is important because if you are looking at bigger solar farms, and then if you're choosing between TOPCon and heterojunction, for example, there's currently no software that can really, like with the real uncertainty, give you a difference in performance. So that inspired us to develop that software ourselves from first principles, and also combine it with this degradation modeling. So we just mentioned UV-induced degradation. That's one, but there's many others that we want to model from first principle and then really help our clients. So we spin out a company for that as well. So it's called Foresight PV, to help our clients to really estimate the differences between performance of various choices, which is cell, so module technology, mounting systems, but also taking into account operating conditions. So like probably in China, it's not as common as in Australia, but we have a lot of curtailment. So a lot of times you have the big power farms. So our grid is not as, it doesn't have as much capacity. So a lot of the time, so in some states, it's now 30% of the time, they're told, don't export, like you cannot export. This actually has an impact on the operating temperature, because if you don't pull out the electricity, so what the inverter does is it switches the module to open circuit. So the energy that was originally exported as electricity is now just generating heat. So these modules are running a lot hotter. Higher temperatures increase degradation. So that's something we quantified for single axis tracker, and they will degrade 40% quicker with curtailment. And so this is one thing that we can help with. We have alternative tracking technology that can reduce both thermal and UV degradation, also improve performance at the times when you actually get the highest value for your electricity. So but it was mainly given by the fact that we want to ensure that all our lab-based work actually is translated to value numbers that people can understand.
Yeah, that's exciting. Well, I'm kind of pretty curious, and wanted to use your model or your software, however you call it, now, because we have done a lot of comparative study on TOPCon versus back contact PC. So let's see what we can do.
Yeah,
put on
so-
your on your system.
Yeah, happy to. Yeah, that's also the collaboration we discussed. So like we've already done great work together on these degradation modes, but you do fantastic outdoor testing. How can we extract the maximum value out of that? Because it's shocking to see that even accounting for the spectrum. So in the modeling you make some assumptions about the spectrum, the actual spectrum that the solar cell sees. So even for silicon, that's a material that's up to 3% uncertainty if you don't properly account for that with aerosol content, precision, the ozone content as well. But then for tandem solar cells, of course, which you probably are testing at the moment, there's so many factors you have to take into account that
like a mismatch thing.
yeah. Now mismatch is one thing, but then so you always have the mismatch. But if you just assume the mismatch at AM 1.525 degrees, and do not take into account how the band gap changes as a function of temperature and luminescent coupling, that's close. It's easily, if they add it all up, it's 10%. 10% is massive. Like if you look at the margin, particularly if you couple it with curtailment. So this is where we would love to work together with companies like JA, because you have a lot of valuable data, and we just want to make sure you extract the maximum value to your benefit from that data. And then, of course, we do our own testing as well. So I believe your testing site is a more moderate climate. So we're looking at testing in our outback. It's very hot, at times humid, and a lot of UV. So having maybe some same modules in both sides would give a lot of insight in terms of yield and degradation. So yeah, that's definitely an opportunity for strengthening our collaboration.
Yeah, that's exciting. We mentioned about back contact and touch a little bit on tandem cell and modules. What do you think will happen in the future? I mean, so let's say in the next 10 years.
Next thing, nobody can predict the future, of course. Now, back contact for rooftop application, I'm very excited because rooftop is mostly about from the fish sea, and all back contact just gives you some more freedom to optimize your cell design to really push that to the limit. For utility scale, I still have to see the numbers, because you sacrifice bifaciality, and of course manufacturing costs, because you will need more steps to produce it, so will be higher. So for utility scale, I would still have to see it for rooftop, and they look a lot nicer. Then tandem, they have to be stable enough, because it's the economics only work if you can produce for a long amount of time. So what that number is, it depends on your internal internal models, of course, but also we have to look at sustainability. So even, using a product for 25 years is still better than after 50 years than recycling. And up to now, perovskite, what are the data that is publicly shared? Of course, there's companies making statements in press releases, but if I look at the scientific conferences, I haven't seen data for really long-term performance. And the National Laboratory of the Rockies is doing probably the most comprehensive public outdoor performance, and most of the technologies there, which a lot of them are from universities, maybe not fully commercially optimized, but they stop performing after less than 80% after 1 year. So we still need some time. I'm not saying that it intrinsically will not be stable, but up to now we haven't seen the evidence. So there's a lot of work needed, and we need to build that confidence in combination with the adequate modeling to really show like the nameplate efficiency or the nameplate performance will be very impressive. But how does that translate to and then you have the difference between 2-terminal and 4-terminal with with 4-terminal being less sensitive to the spectrum, so probably able to maintain its good performance.
Yeah, but it's more complicated in terms of module design.
Module design and system design is more complicated, so I still think there's a lot of work to be done. But my main message to the market would be, ensure that it's stable, and don't believe that IEC testing is good enough. So the current IEC standards are made for silicon modules, for infant failures for silicon modules. So for perovskites, there are new failure modes, because there's a lot of new failure modes that were never seen for silicon, so we need appropriate testing for that. So there are testing protocols for that, but often in press releases, as he quoted, we passed one of the IEC tests, and then that's of course misrepresenting what the product can really do, because if you cherry pick your IEC tests, or if you say we pass all the IEC testing that was made for silicon, that doesn't guarantee, and IEC testing never guarantees 25-year performance. It just means we do not have the most widely known failure modes that are tested in IEC testing. But if you would not pass IEC, you would typically fail in the field in a couple of years. So,
Yep. So let's see what's going to happen in the future. JA, in our R&D center, we are developing back contact cells and modules with different formations, like hybrid with or pure poly-based TOPCon and hybrid. We just actually in the very beginning you talked about the selectivity things for N and P. Then we see if we can address the problems separately and find the best contact passivation material for N and P. So we have back contact formation, and Professor Hoex just mentioned about challenges and different opportunities on 2-terminal and 4-terminal formation, and perovskite with the heterojunction or TOPCon as a bottom cell. Well, the challenges and opportunities lies on all the options. So you said you cannot make accurate prediction. I think so. Neither could I. So what JA has a responsible the supply manufacturers, we just do all, right? We in R&D we do all, and we have to make sure we deliver the best and most reliable product to our customers for a very long time. Not just we've done fantastic job in the past, and we are doing pretty good job now, and we will keep delivering in the future. So Professor Hoex, if you have a few, please can you give our audience some take-home message? Like, what do you think the industry,
I did, yeah. So,
or JA, or
Jay, yeah. I think I just want to come back to one of your last statements. So, Jay is, I've seen and I see it as a quality leader. So, of course, you're working on all technologies, which you would only, yeah, really sell a product to the market when you believe it's ready to be stable enough. And also like UNSW, we work heavily on, we actually have the perovskite single junction world record at the moment with our partners in China. So Suzhou University, yeah, probably mispronounce it, but you can check the efficiency tables. And we hold the world record for.
we also work pretty closely with them on different topics.
Yeah. So we work on every technology, but also, yeah, that's why we also know them intimately. That's a big advantage. So there's many different options. And I forgot to mention building blocks that we can still add to silicon to, so like up and down conversion. There's very different flavors. And there's definitely now a resurgence in that research. So there's to add building blocks that are not an additional solar cell, but like photon converters. So either two low energy photons into one high energy photon, or a UV photon into one or two additional photons. So or electron hole pairs. So there's never a shortage of ideas, but of course the industry is now, we're in the solar winter. The winter is lasting longer than I think anybody wants, but that also it puts a very strong pressure on cost, which and now with the silver prices, that's of course a concern. So that's determining the direction of the industry. It has always been, but now I think we're getting closer to the fundamental limit. So in terms of efficiency potential, it's limited because with the silicon node, but cost reduction is definitely the very strong focus. But it's amazing how quick the industry has grown. So with close to 1 terawatt of production, silicon is going strong, and also it's already delivering. We should also not forget it's delivering the cheapest electricity on the planet.
Yep.
Already. We can make more cheaper, so higher efficiency will help us with that, because silicon has already reached a very, very nice level. So I think I'm very excited of what's happening with the industry. You keep the industry, and JA Solar keeps surprising me with new innovation. So like the fact that you've been able to achieve close to 750 millivolts with TOPCon. Like, I think if you would have asked anybody 3 years ago, nobody would have been there would not be many people say like, so TOPCon can do it. But you guys have done it, and with very clever innovation. So and that's also what's happening now. A lot of you quickly, and then it can be a collaboration with academia, but often on the TOPCon front, a lot of the innovations have come from the industry players. Like the developments in the silicon material, we didn't even touch upon it, but like the lifetimes, so that's the electronic quality of the silicon material that we have now is just amazing. So the innovations you have done there, so it never stops amazing. So it's a very exciting time. Although it's solar winter, the innovations keep going, and it's companies like JA who invest a significant amount in R&D that are driving that. So very happy with that.
You see, just in the last second, we find we have more topics. We have
many more topics.
Yeah, we have. So whenever we start talking about technology, is kind of never ending. But I think even the camera's battery is running out. So it's very. I'm very happy and honored to have this opportunity to chat with Professor Bram Hoex, and is a world leader and world expert and in his field. We talked about the silicon solar cells. We talked about in the future perovskite silicon tandem solar cells, and we talk about different applications like whatever in underground and whatever in the space, the challenges and how we tackle the challenges, and it has been very, very inspiring, and I have been inspired. Thank you very much. And I think also we have to stress again that the industry leader will have to work even more closely with leading university like University of New South Wales. We keep innovating and developing new stuff, just as our JA Solar's mission, developing solar energy for the well-being of humanity. Thank you very much.
Thank you.
Thanks, Professor.
Cheers.
Thank you.